Let me start my presentation. The title is GenDOM, Generalizable One-Shot Deformable Object Manipulation with Parameter-Aware Policy. First of all, I'd like to quickly share the kind of task we want to solve in this research. In this video, the robot arm is spreading out across. The cross is made of cotton and it's soft, so that the robot needs to move with a certain amount of acceleration. In our research, we aim to enable robots to take actions based on the characteristics of the cross, such as stiffness and softness. In the demo, by applying the appropriate acceleration according to the softness of the cross, the robot successfully spreads out the cross. These tasks are particularly difficult because they require an understanding of the object dynamics before any manipulation. Applying incorrect force can lead to significant and unpredictable deformation of the object. Humans can easily grasp these dynamics because with just a few trials, like swinging the object, or they may already understand the dynamics from previous experience. The question then arises, how can we enable robot to achieve dynamics manipulation of various deformable objects such as lobe and cross? We propose GenDOM, which consists of two parts. First, training an augmented policy with diverse parameters in a simulator. Next, estimating deformable object parameters using gradient-based optimization. This is an overview of our method. In the simulation, as shown in A, we pre-trained the task policy by randomly sampling parameters. Specifically, our research concentrates on Young modulus and Poisson's ratio as parameters that determine the characteristic of a deformable object. This approach is similar to domain randomization, but the key difference is that we use these sampled parameters directly to train parameter condition policy. Subsequently, as depicted in B, we employ the gradient-based method to optimize the parameters, specifically Young modulus and Poisson's ratio, for real-world deformable object. Since the pre-trained policy is conditioned on these parameters, it can generate actions that align with the object dynamics. Therefore, we refer to it as a parameter-aware policy. Let me summarize the GenDOM framework once again. In a broad sense, it can be considered as a real-to-symmetry approach where we condition the pre-trained model in the simulation with parameters obtained from real-to-sim. With this framework, the gradient-based parameter estimation enables first parameter optimization from a small number of real demonstrations. By directly conditioning on these parameters, that can perform parameter-aware manipulation of object. I will share more details of a parameter optimization method. For parameter optimization, we carry out a predefined lifting action on the deformable object, both in the real world and in simulation. During this process, we store the point cloud from the real world and the simulations. We use a gradient-based simulator to minimize the discrepancy between point cloud in the real world and simulation at each time step. By optimizing parameters to minimize the discrepancy of a point cloud, we identify parameters in the simulation that replicate real-world behaviors of the object like lobe or cross. Here are the qualitative tests to determine if the optimized parameters achieve realistic behavior in the simulation. We tested two different types of lobes, polyester and cotton, and released them from the different point upper, middle, and lower. On the left side, you can see the optimized behavior in the simulation, and on the right side, the corresponding real-world behavior. Notably, they exhibit mostly identical trajectories. This indicates that we have successfully determined appropriate values for Young modulus and Poisson's ratio, effectively capturing the dynamics of a deformable object. Then we trained the policy in simulation and applied it to the real world in a zero-shot manner. In this task, the goal position where the lobes should reach is given, and the robot must release the lobe at an appropriate position so that the lobe reach the goal point along gravity. The upper part shows our method, GenDOM, which runs the policy only in simulation and further conditioned it on the estimated lobe parameters. The lower part shows the policy run using actual real-world demonstrations. The horizontal axis shows a different goal position, which is gradually shifted. As a result, we find that there is almost no difference in accuracy between GenDOM and the policy run in the real world. Although our method uses only one demonstration for parameter estimation, it shows nearly the same accuracy as the policy that uses 100 demonstrations for running. This means that GenDOM significantly reduces the number of real demonstrations required for running. Similarly, even when the lobe is changing, our method can achieve high accuracy because it learns by directly conditioning on various parameters within the simulator. The baseline method does not condition on lobe parameters, so it cannot adapt to change in the lobe. Looking at the result, we can see that our method shown in the upper part can bring the lobes and closer to the goal line. We also conducted the parameter optimization and tests on the both cotton and rubber cross. The left video displays the real-world behavior. The middle shows the behavior in the simulation with optimized parameters, and the right slide presents the same simulation behavior, but converted to the point cloud for visualization. As cotton is more flexible than rubber, you can observe in the point cloud that the cotton sags more and is more friable when lifted compared to the rubber. Using optimized parameters, we conduct cross-spreading tasks. The upper part displays results from our parameter-aware policy, while the bottom part shows results from a non-parameter-aware policy. We tested spreading both cotton and the label cross with dynamic motions. As cotton is more flexible, it requires relatively quick movement. In contrast, rubber is stiffer and already somewhat extended, so slower movements are ideal, especially when considering the risk of robot malfunction. The red numbers indicate the acceleration ratio, expressing how dynamically the robot moves. In the bottom section, the non-parameter policy displays the same ratio for both cotton and labor. This is because this policy cannot alter action control according to cross type, lacking parameter awareness. Conversely, in the upper section, a policy adjusts behavior based on object type, resulting in high acceleration for cotton and lower acceleration for rubber.